Okay, we're live. So, Devin, do you want to introduce yourself?
Hello, I'm Devin Castellucci. I am the lead fabrication mentor on Team 1678 Citrus Circuits. We won the World Championships, not this last year, but the year before, 2015 season. And I have been a part of Citrus Circuits, let's see, for 11 years now. This is my 9th year that I've mentored. I was on the team for 2 years as a student. And basically, this is an opportunity for you guys all to pick my brain about what I know about how our team is run and the various mechanical insights that I've picked up over the years.
So, I have a mic, which I'll give you. That way it goes through. So, who wants to kick us off?
We'll introduce ourselves.
Yeah, because there's only one team here.
This is Project Bucephalus. This is Project Bucephalus, Team 5985. We've been doing FLL since 2010, but this is Stronghold is our first time doing FRC. So we have blank slates, teach away and myself.
Did you get all that?
The last little bit, not so much. It's a little echoey, so you have to speak pretty clearly.
Can you hear us okay now?
Yeah.
Okay, so we are Project Bucephalus, Team 5985. We've been doing FLL since 2010. This is our first year at FRC.
Okay.
Blank slates, so teach away.
So, for a new team, one of the biggest decisions you have to make is what your build style is going to be for how you approach building your robots. Every team is a little different. It's based a lot on what tools you have available and what knowledge you have on how to use those tools. And once you figure out more or less how you want to approach making your robot, you then need to train your students and potentially mentors on how to execute on that particular style of building. So,
You want to explain what we've got left? Yeah, it's always how we set up what we got.
Alright, so what do you use like robot?
Hop in the front. Move in the front seat so we can hear you. So, yeah, what tools we got, where we're set up, etc.
So basically we've only got the basic tools. So we've got drill press, drop saw, bandsaw, drills, all that kind of thing. So nothing too fancy. Yeah, at the moment we just went for like a simple yet solid robot. Nothing like, we didn't do a high goal shooter or anything. We just had an arm which could lower and do stuff. So basically push balls out of the way or do the portcullis and all that kind of thing. Yeah, that thing. And we would suck in.
here, hold up. Start over from portcullis. It lagged out.
Alright, so we can do the portcullis and basically we can suck in balls and take shots at the low goal, and that's about it.
So, other than build style, how you're going to approach doing your build, another thing that we find incredibly important is on Citrus Circuits, we spend the first day or so. Every single person on the team reads the rules front to back. And I don't mean skim, I mean actually read everything. We then test all of the students and mentors on those rules so that we know that they understand them. And then from there, we figure out what strategy we want to execute during the game, what we think is going to be what we think is going to give us the best advantage during a competition. So this year it was having a robot capable of going into the low bar, being able to solo breach, ignoring the drawbar and portcullis, ignoring the drawbridge, and what was the other one? Sallyport. Ignoring those two going forward, but be able to do them going from courtyard back, and be able to do a 2-ball autonomous was kind of our stretch goal for that. And be able to shoot into the high goal from the defenses. There's more in there than that, but that was the basic part of it. So we figured out that's what we wanted to do. Now, how can we do that with what we have on hand and what we know how to build? And then that's the next day or so after we've figured out the strategy. So you can do a remarkably large amount with very little. I know this in particular because we might be a well-known team now with good resources, but just a couple years ago we were working out of a 20-foot shipping container as our main shop, and we were still making highly competitive robots with what we had. So figure out how you're going to build, figure out what you want to build, and then figure out how to build that with what you know is, I guess, what I'm getting at with that.
You were talking about build styles at the beginning.
Yeah, so your build style kind of depends on what tools you have at your disposal. So we have a CNC router and mills and lathes. So our build style is kind of a pre-drilled aluminum extrusion tubing frames held together by drilled and cut sheet metal gussets, riveted together. And our drivetrain, for the past several years, we've done West Coast Drive, which is a cantilevered wheel outside of the frame, the structural frame of your robot. So the wheel is only supported on one side of it, and then it goes through a piece of extrusion tubing and has two bearings supporting the shaft, and then it's sticking out. There's a lot of advantages to them, but there's a lot of resources online that you can just look up, particularly on Chief Delphi, discussing the merits of that style of drivetrain. Previously, before we had those, a lot of what we used for our builds was 80-20 style extrusions, where you can put T-nuts in and tighten things down and move them around, which is really good for prototyping. But during competition, it can be kind of hard to work with because it's a constant battle making sure everything stays where it's supposed to. And there's other teams out there that basically do bent laser cut sheet metal parts for their entire robot frame, chassis, superstructure. That's what I mean when I'm saying build style. So you want to determine what's easy for you to make and make well. So what you guys have is similar to what 1678 had in about 2012 and earlier. We relied on 80-20 for some things. We used a lot of plywood because it's easy to shape, easy to change, easy to modify on the fly, and it's sturdy. We also still used a lot of stuff like aluminum angle and extruded tubings. Measured out, cut, drilled into whatever we needed. Yeah. Anything you want me to further clarify with that?
That's what we were doing a bit. But yeah.
Can you hear Zach all right?
Sorry, say again?
Yeah, move to the front then. You're too quiet. Hang on.
Move close to Marcus.
Yeah, so we were doing that sort of thing with plywood a bit, and then we moved on to using metal in the later parts of developing the robot.
So one thing that I have found to be an absolutely amazing trick that really helps out is if you have access to a CAD program and a printer, you can pretty much make whatever flat pattern you can fit on a sheet of paper. You can design a gusset in CAD that's going to be like a gearbox or some part of the robot support. And then you can print that out onto a sheet of paper, 1-to-1 scale, and then glue it on to whatever it is you want it made out of. And then you just cut to the lines, center punch and drill the holes to the sizes that you need, and you have your part. And I have used that one for many, many years, and it is still something that we use a lot during prototyping if we just want to get something done really quick. For something more like the extrusions, one thing I like to do is scribe it with a pair of calipers to the dimensions and placement that I want for drilling holes and such. And then a lot of the assembly, the downside to approaching it in that way is it's very hard to make exact replica parts, which is one of the big advantages to having the CNC type capabilities. We'll actually send out some of our stuff to a few different sponsors that will laser cut or machine some of our components that we get designed really early in the year, just so that we don't have to do it. Pretty much our entire drivetrain on our robots was done in that way, so that we didn't have to machine it in-house.
Would you CAD the whole robot before you built it, or would you prototype with physical objects?
Yes. So after we figure out what it is feature-wise that we want our robot to have, we go ahead and prototype some of our ideas about how to make those work. We make a mock-up of it, see what affects what, For instance, this year we knew that we needed to have a shooter for our ball. So we did a one-wheeled shooter, put into an 80/20 frame, and we figured out what speed we needed to be able to hit, how much compression we needed on the ball, the approximate angle of the hood, and stuff like that for it. For our intake, we made a mock-up of it, of how we thought it might need to go. Built it really crappy, sort of, and figured out, okay, this works, that doesn't work, we need to change this. And once we've sort of gotten a successful version of the prototype that's doing what we need it to, we copy the dimensions over and any other information we need, and then we CAD the finished mechanism, or nearly finished mechanism, based off of those measurements. And then we go ahead, we build that, we put it together, and then hopefully it works. If it doesn't, it's usually very close, and then we tweak it around until it works, or we figure out, oh, well, this one thing is messing up the entire thing, so we need to go back, change a few parts, try it again. And the whole process is designed to, as our lead technical mentor would like to say, is fail faster. So every time you fail, when you are trying to do something new, you have the opportunity to learn something from it. And that's one of the reasons why we try and do as much stuff as quickly as we can before we actually flesh out the whole robot itself, because we want to see what works and what doesn't work so that we can move along through our build season without wasting time. And it's also important for us because we have a pretty large team, especially around the start of build season, and we need to keep everyone occupied.
What
So-
CAD program do you use?
Primarily we use SolidWorks. I know you can get licenses from them as an FRC team for free. It's the student version. There's a few other things we use. Trying to think. I think SketchUp is one of them that we use a little bit. But for doing the actual robot itself, we are using SolidWorks. We use AutoCAD for doing a lot of our sheet parts for like sheet metal gussets and the belly pan for the robot. Mostly because it's a little bit easier to work with Autodesk doing that kind of thing than it is to work with SolidWorks. And we're exporting it as a DXF file, so it doesn't really make a difference between the two.
So what do you guys use? Earlier you were saying you riveted the stuff together. Do you prefer rivets over bolts? Or?
Mostly we use rivets in places that are going to be pretty much permanent. You can drill rivets out if you need to replace a part. It can be a little annoying, but another advantage of rivets is they're a lot lighter. If you put a bolt in the same hole you're putting a rivet in, the bolt itself is going to be heavier. The head is going to be larger than the head of the rivet, and on top of that, you need to put a nut on the back side of it. But there's still a lot of things that we use nuts and bolts for. mostly on longer connections and things that we need to be removable. So rivets is pretty much just the frame. Bolts are used to connect the frame and the superstructure and the drivetrain together. And then depending upon what's in the actual assembly of a particular part, like the shooter, some of it could be riveted together, but more likely than not, the actual assembly is going to be held together by bolts. It makes it a lot easier to service that way.
So when you use bolts, you use like spring washers or dual lock nuts or what kind of stuff?
We use nylon lock nuts for pretty much everything. We use alloy steel bolts, and one thing that's fairly important is to try and standardize within just a few different sizes of hardware what you are going to be using for building your robots, because one, it saves a lot of space for your hardware, and two, it means you only need a few different tools to do pretty much everything you could need to on the robot. We use quarter 20 socket caps and 1032 socket caps for the majority of our robots. There's a few other hardware sizes we use in there, but it's a very small fraction of what we do.
Do you guys play with vision tracking or laser rangefinders or things like that, mate?
So this year we did do vision tracking, and trying to think other years that we did as well.
Well, let me ask the question the other way. This year the kids did simple, strong, and they did very well with it. That pretty much sums up. It's a kit bot built simple and strong with a few added flares thrown in. So we've got, what would you advise we start looking at? Pneumatics, vision tracking, anything else to start with stuff?
So there's a couple ways to approach the vision issues. So we approached it as an automated system because in order for us to be able to pull off a two-ball autonomous mode, it was required for it to be able to aim itself properly without our help. And the only way to do that is to have it actively vision controlled. But there's plenty of other ways to accomplish it. You can just one of the most successful ones that's not vision tracking that I've seen implemented over several years of different games is a flashlight.
Okay, explain how that works.
So your robot typically needs to be in a certain range from what you're trying to hit, as well as in a certain alignment. And you can put a flashlight on your robot so that it hits a particular spot that your drivers can easily see when it's lined up appropriately. So this year, I've seen a number of teams do it where they had their flashlight aimed so that when their shooter was aligned, it would be basically sitting right in the middle of the high goal. And then they'd know, hey, I'm lined up, I'm at the appropriate range, take the shot. And then it goes in. Some other teams this year did it so that it was aimed lower, where they just had a particular spot on the field that they know they'd have the right range. And then from that, they just needed to make sure that they were properly aligned. And they'd have it aimed lower down on the tower, which is a little easier to see. In 2012, they had the retro reflective tape again that year, and we had a webcam on our robot. And sitting in front of that webcam, we had a little post that was on a spring, so if it got knocked around, it'd come back into the right position. We had a green LED light ring sitting around the webcam aimed forward. So when we were looking at the goal that year, it would show up as this bright green box. And then all we'd do is put ourselves at the right spot on the field and then put the black line in the middle of the green box. And the drivers had the view of the camera set up so they could align that way.
How do you stabilize the camera so it's always looking straight ahead?
Put it on the robot in such a way that things aren't going to hit it. And then just make sure that it cannot move.
We're using the Microsoft webcam, and it's got like the camera and the thing that attaches it onto stuff. It has a little hinge. And
Yeah. So that one, one of the other teams that I mentor, Digital Minds, we're using the same one. The way I solved that was a large quantity of duct tape. We had them mount it, and then we had the robot set up so it was looking at the right spot with their robot aligned where it needed to be for the goal, and then we just kept taping it down until I couldn't move it anymore.
How many times a week or a month would your team meet, and how long would each meeting last for?
So our typical meeting schedule, just during the majority of the year, excluding summer, is Wednesday and Thursday, 6:30 to 9 p.m. Main reason for that time is so that us mentors don't have to go into work stupid crazy early to get out at a more school appropriate time, which has been really nice actually. And then during the build season and competition season, we typically add on Saturdays and Sundays 9 to 5. Sometimes we will add in extra days. Sometimes we will stay a little later. It depends on what we're doing, how effective we're being at working at the time. But this year we did fairly good at staying to those days. Not much else was needed outside of that.
How many mentors and team members do you have, and what have you found to be the best number?
Sadly, that's not a simple answer, but I will answer for you. So we have our whole mentor base and our whole student base, and then we have sort of our core mentor group and our core student group. So our core mentors, let's see here. I'd say 5 or 6 of us. We have Harvey, the coach. We have Mike, the technical lead. Myself, the fabrication lead. Anthony, who also helps out with the mechanical team mentoring. And either Brooke or Richard, which are business and media team leads. We do have other mentors, but they aren't as time invested as us. The mentors we have outside of that are probably somewhere around 15 total, I would say, including ourselves. In terms of students, I believe we had 80 students on the team roster at the start of build season. But as anyone that's been on a team for a few years can tells you, that does not reflect how many are there at the end of the season. We probably retained 50 to 40 kids fairly well during the build season. And during the competition season, it was probably down to around 40, with like 25 or so kids like really dedicated to the project.
Sometimes some of our team members they don't focus very well or get tired really easily. What you as a mentor would do to like prevent the students from getting really tired and focusing on the thing?
That's something that a lot of teams really do have trouble dealing with at times. I know we do. We've gotten a lot better the last few years at it. Most of what we do is we sort of set ourselves up in a way that if someone's working on something and someone's not working on something, that person that's not working on something will go help one of the people that's working on something, even if they don't necessarily need the help. Because a lot of the people that have a hard time staying focused are a lot of the newer members, and part of the reason is they don't know what it is they're necessarily supposed to be doing. So by bringing them in and being all like, hey, hold this, help me tighten that, let me show you how to do this, it sets up sort of a peer-to-peer mentorship style that we've really been focusing on these last few years, which has been particularly important for myself. I know a lot of stuff to be able to teach all of the students we have on the mechanical team, but I cannot teach 30 or 40 kids at a go very well. And even working on smaller projects, it's still very difficult for me. So what I do is I work with a number of students, and then over time they get their skills improved to the point where they can then turn around and do a lot of the same stuff I was doing with them, with younger and more inexperienced members of the team. And we really make a point to our students that it is very important that we approach it that way, because it keeps everyone engaged, it keeps everyone learning, and it helps the team retain its knowledge base, which is very, very important. I've seen a lot of teams over the years that had phenomenally good runs that I can attribute to like one or two people that were on that team, but when they leave, they lose that knowledge base that they were providing to the team, and the output, the visible output from that team diminishes over the next few years because they failed to retain that knowledge as a team.
Okay, so just going back to the cameras, I'm one of the drivers, and when you're driving, I found it gets very laggy and it's a bit difficult to see, or it's a bit delayed or something. So Do you guys have that problem? Is that normal, or is there ways to fix that or improve it?
So, unfortunately, this is kind of an electronics programming question, which I'm not very good at. It's just what I've sort of gotten secondhand off of the sub teams we have working on those. But this year, we did have a fair amount of lag that we were dealing with our auto aim code, and the way we solved that was by getting a coprocessor on the robot. So something like an Arduino, the Kangaroo PC, to do the actual computing for the vision tracking on the robot itself. What we had been doing is we were sending that camera information back to our driver station computer. It was crunching the numbers and then feeding the output back to the robot. And then, even though it's just a little bit of lag on each one of those steps, it adds up to being rather noticeable by the time you're trying to get it to do something in a 2.5 minute match. If you can cut out a bunch of those steps, it dramatically improves the speed.
So basically, you're just using the Arduino to do all the heavy lifting, and you're minimising the information being sent across the wireless.
Yeah, and it reduces the bandwidth load over your robot's radio, which is a good thing, and it means that the robot, from the point of view of the robot's control system, has a lot less to deal with, as well as your driver's station computer has a lot less to deal with. So,
Just a last question.
On the lag issue, have you ever tried running with a second camera?
have I ever tried what?
Running a second camera.
Two cameras at once.
No, I don't think we have.
You guys tried doing it.
We saw another team there that's reversing camera.
Yeah, so one team these guys saw had a reversing camera as well as a forwards camera.
Yeah, I mean, I think that's more just to improve the field of view. And it would depend somewhat on what you're trying to do with all of that. I know there was some robots this year that were trying to have automatic ball tracking in order to locate balls on the field. And I could see 2 cameras being really useful for that if the direction you're shooting is different from the direction you're intaking from, like it was for our robot. We intaked with the back of our robot and shot from out the front.
When you have the drivers, and you like have the pair of drivers or only one driver, if this driver or drivers are really good and apparently you realize they're better than the other ones, would you still shuffle the drivers around so everyone can have a go, or everyone will just stick with that good driver?
I'm trying to think if we've ever really changed up our drivers. Pretty much the entire time our team has been around, we've had a fixed drive team. So we had a driver, an operator, and a human player, as well as our coach. And they pretty much just stuck with those roles, because I've seen a lot of very good robots underperform at events, because the drive team wasn't able to get hours and hours worth of practice in with it to get really good at it. And another thing in terms of drivers and operators that's very, very important with a programming and operations standpoint is you want to try and take away any thought that you can from them needing to operate it. So if they have to line themselves up just right and then get up to the game piece and then do a couple things in sequence correctly, that's a bunch of things that they have to get right in order to do what you're trying to do. Whereas if you sort of set it up in a macro style system where I am now where I want to be, now do all of these things for me by pushing this one button in the proper order, it makes it way easier for the driver and operator, which is one of the reasons why we try and avoid any system that's got a continuous adjustable system on it. Basically, we have it set up so that it's in one of it, 2 or 3 different positions, and it's just those are the positions. So that way they don't have to try and move the arm up by sight to a certain point and then they go for it. It just position 1, position 2, position 3. Which is another reason why on our team we have a very serious thing for rolly grabbers. Which we like to describe as touch it, own it systems. You touch the ball, it is now yours. It goes into the robot, goes where it needs to go, and it's just done. All you have to do is make contact. Which is one of the reasons why I really dislike claws. Because you have to line up on it just right, actuate it, and have the chance of needing to try again. Whereas if it was on a rolling type intake, even on a claw that's got rolling intakes on it, you touch it and whoop, got it. So that's what we try and do for our drive team to give them the most experience and the least load to accomplish their job.
So you're saying that when you're designing the robot, you'll see what you know how to do and do it well. But how much kind of risk would you take when you're, say you want to build something but you don't know how to build it yet?
That is an excellent question. So the way we approach that is we don't build anything that we don't have prior experience with. So let's see here. So for the 2014 off-season, we built a off-season robot that had an elevator on it. That was the first time we'd ever built a proper bearing on tube style elevator. And turns out we got very lucky because 2015 was the game that it was, and we needed basically a robot that had a nice, well-built elevator. 2015 off season, we went. Go ahead.
Oh no, he's on the phone.
Ah, okay.
2000.
Marcus Isaac.
Driving a match.
Marcus Isaac, head down. Everybody else stay put.
So our 2015 off-season robot, we made an articulated clawbot. We'd never done an actuated style claw or arm off of a motor before. So we did that, and we ended up implementing that this year by having our entire arm elevator climber assembly utilizing that type of system. So some things we've seen from other teams, either in person or via pictures online, that we feel rather confident that we can pull off ourselves. And then for other things that we don't really know the nuances of them, we go through, we build it with some intended goal and figure out the little things about what we need to do to make that system work for us with the tools and equipment we have on hand to make it. And one of the sayings related to that whole thing is, we like to steal from the best and invent the rest. So our 2013 robot, the Frisbee shooting robot, is a good example of this. Our first competition, it was a straight two-wheeled inline shooter. It worked, but it was not the best. So we decided after that event, we want to make a different style shooter for this. So we copied, I believe it was 973 that year, had a partial arc one-wheeled shooter. We implemented that at our next competition, and we were pretty happy with it. And there we took a look at our intake system, and we went to ourselves, this thing could work a lot better. So we ended up copying Team 254, the Cheesy Poof's intake design that they used that year. So by the time we got to championships, the only part of that robot that had not been changed or altered was the drivetrain.
Before building a robot, did you ask for any opinions or just got inspiration from other teams?
So it depends a little bit. I would very much suggest, if there's teams in your area, to sort of be generous in sharing the ideas that you have, because in the end, they give you input, you give them input, you end up giving each other an advantage to competing in that competition. And a lot of the like looking at old designs that have been done before, I mean, it's basically just looking around and seeing what other people had done to solve a particular problem. So in 2013, that was a very interesting design challenge year, because the game piece was Frisbees, which was a very, very different style of game piece. Pretty much everyone's ideas on manipulation of game pieces got thrown out the window because no one had done it before. One of the biggest difficulties for us that year was figuring out how to pick a Frisbee up off the floor reliably. That was not easy. And we did look at other robots as we went through the events in order to see, hey, I think we can improve this thing by changing it around a little bit, because it seems to be working better for them. And basically just applying the stuff we pick up over time.
I think we're about to collide, so.
Yeah, unfortunately, we're out of time, so I'm going to end the broadcast here.